Welcome back. So a wave and its speed in a uniform string. So now what do we mean by a uniform string? Think of kind of like a guitar string that you would have that you can actually play music with. Now that guitar can be vibrated, kind of plugged back and forth. And for uniform, we are referring to that it has pretty much the same thickness throughout and it has the same density. Now, in these particular strings, we can extend the universal kind of wave equation, which is the equation for speed. Now, I've talked about this equation. I can put up a link up above there, and you can relate the actual speed in various forms. So you have a wavelength divided by the period, or you can simply designate it as frequency times the wavelength. Now, in a uniform string, what is very interesting is that if you take a string, so within here, so I'll come back to these equations. So if this is the actual string that you have, and it will have a certain length. And as you can see there, it has pretty much the same thickness all the way throughout. And we assume that it has the same density. So it's pretty uniform. So it can actually create the same music vibrations as it goes through. So we can take, instead of, as we know, density is related to mass divided by volume. I can put up a link to density up on top there, so I'll assume that you're familiar with density. However, when we're talking about strings and that they're uniform, so A, if the thickness is uniform, it doesn't matter where you slice this, they will always have the same exact thickness, and it will also have the same kind of surface area within. So if you slice the cross-sectional surface, it's going to be identical. And therefore, so within here, so we can say that this density is nothing else but mass multiplied by the cross-sectional area and then times the length. Well, if you do have uniform objects like this, then you can actually, instead of the cross-sectional area, you can remove this cross-sectional area because it's the same. And you can call this, which is going to be the actual mass of the entire thing, divided by the length that you have. Now, that right here, we call the linear kind of density that you would have of an object. Linear because it's in one particular dimension, so it's one-dimensional, and it's only relating the mass to its length, and it doesn't really worry about the volume. So, well, strings can be captured in this way. All right, so that's the first thing. So you have this equation right here, and you have this mu. So mu, you have this Greek letter right here, and it is related to the mass over the actual length. So again, in terms of the string, instead of utilizing the density, which is the true density, okay, on the volume scale, we simply take whatever the length will be of this object and the mass of this object, we can divide the two, and we can figure out what the linear density is. Once you have the linear density, what is very interesting is that if you take these strings, you can calculate the actual speed of the wavelength that passes through them. Now, you might say, well, this looks very simple. You just take the frequency and you take the wavelength. That is true, right? That's correct. This is the general universal wavelength kind of wave equation for speed. However, you can find this exact same thing for kind of constant uniform strings in this way. You can take the square root of the actual force of tension in the string. So you can think of the guitar. That guitar, okay, will have a certain tension in it that you're passing through. So if you know what this tension is, and then you know what the actual uniform here, the linear density is of that string, you can divide the two and you can take the square root and you can find what the speed is. Now, this of course is much more complicated than the actual equation for speed. So this is much, much simpler. But we don't always have this luxury of the frequency and the wavelengths that we have. And more so, if we are interested in having our strings to be able to move and propagate waves at a certain speed, we may know what exactly their density is because we create them. And then what we can do is we can tune, like you tune a guitar, to a certain tension. And if you tune it to a certain tension where you have a certain linear density, then you can actually hit whatever speed that you want. And that particular speed, of course, is going to be now related to the frequency and the wavelength. So you can create music, okay? And you can have certain tones that you actually want by properly tuning what the tension is. So that is very neat to be able to see that. Now let's see this in action, all right? Now, before I give you an example, I just want to mention to you and convince you, although I'm not going to derive this equation here for you, but I just want to show you that indeed doing this is going to give us the actual speed. So now a very nice quick check is just to check what the units would be. So if you take this actual equation and you take a look and you recall that the force of tension, the SI unit, is newtons. Now newtons, if you go way back, is nothing else but simply kilograms per meter second squared, which is mass multiplied by acceleration. Now this, which is your linear density from up above in terms of linear SI units, you can see there that what we have is, this is nothing else but mass, which is kilograms, and this is nothing else but length, which is meters. So if you take these two and now you divide them, and you have this, which is kilograms, and this is now per meter, like so, then what you notice is that the kilogram and kilogram will cancel. This meter is in the denominator, So when you do this, this is going to come up here, okay? And we're going to obtain meters squared all over seconds squared. And now if you take the square root, then notice that the square and the square will come out, and indeed you get meters per second, which is your SI unit for speed. Now this is just a dimensional analysis of units that you have, just to double check. It's not a derivation that this indeed is your speed. Okay, so that goes beyond this video, which I don't necessarily want to go to. So for you, I want you to know that if you take these uniform strings, you can find out what the speed is by knowing what the tension is and what the linear density is. Or if you know or you want a certain speed, then you can find out what tensions are. Let's dive into an example. Here is a pretty nice little short example. It says that we have a uniform string of length 180 centimeters. All right, so let's write this down. So our length 180, so I'm going to change it back to metric units, 1.8 meter. It has a mass, so this has a mass of 235 grams. Again, I'm going to change this back to metric standards, so it's going to be 0.235 kilograms. If you would like to have a wave propagate through this string at a speed of 100 meters per second, so that's what we would want. Now, of course, there's no tension, really no propagation that would actually happen, right? So that's what would happen. So we have to kind of tune this up. So we have to create a certain tension to be able to see that this actually follows through and propagates 100 meters per second. Is pretty quick. So let's take a look how we would find this. So how in the world am I going to find, and here it's asking me what is the tension in the string that would be needed. So if I go back to the actual equation, it says that V is equal to the square root, and this was the force of tension divided by your linear density. Now, I know what this is. They're telling me this is 100. Now, my linear density right here, I can certainly find because this is mass divided by the length, and I have both of them. So the mass, which is 0.235, that's kilograms. The length, which is 1.8 meters. Now this gives me what my linear density is. So the only thing missing here is my tension, and that would have been right there. Now, if you take this formula and you substitute everything back in here, then what you'll notice is, now in terms of having the square root, you can square both sides and you're going to obtain V squared is equal to force of tension divided by mu. So in other words, if you multiply both sides by mu, right? So in this case, if I multiply both of these by mu, then this is going to get rid of this. And you're going to get that the force of tension is equal to mu and V squared. So let's try this. So I know everything within here. So I know that my mu is 0.235 divided by 1.8. I know that my V, the desired one, is 100. So this is going to be squared. And I can find out what exact tension I would need in that string in order for this to work out. So let's see this. So I'm going to put this back in, 0.235 divided by 1.8. That's that. Multiplied by 100, and this is going to be squared, so it's going to be rather big. And what you notice is you get 1, 3, 0, 5, 5, 5, 5, etc. So this is repeating newtons, and you can round to whatever it is that you like. So about 1,300 newtons of tension that you would need, which is, quite a bit of tension that you have. You can certainly change this to pounds if you wanted to, okay, in order to see how this would work. But that's quite a bit in terms of the tension. So that equation that we have is pretty useful because it allows us to tune, right, the actual tensions to the desired things that we want. So there you go. That's the introduction to these, which are speeds within strings that are uniform, and you can relate them back into linear densities. Thanks for watching. We'll see you in a future video. Bye, everybody.